First question, where do you find protons and neutrons?
An atom.
In the nucleus.
In the nucleus, exactly. So if this is our nucleus, and we have protons and neutrons, what do we have around, what don't we find in the nucleus?
Electrons.
Electrons.
That's not really true. There are electrons in the nucleus, but I will get to that. But the electrons that are involved in chemical bonding are found outside the nucleus. We actually know that there are electrons in the nucleus because certain types of radiation are the emission of electrons, and they come from within the nucleus. So actually, what a neutron is a proton and an electron stuck together. That's why it has no charge. And when an electron is released as radiation from the nucleus, that neutron turns into a proton, and then that element, which is spit out an electron as a bit of radiation, becomes a new element because now it has a different number of protons. So that aside, and we'll probably get to that when we talk about radiation a little later in the term. So how are protons and neutrons the same?
Yeah, mass.
Their mass is close. Their mass is almost the same, but neutrons are that tiny much bigger because they have the extra mass of an electron associated with it. But since electrons are about 4,000 times less mass than a proton, yeah, the difference is extremely small. So right, so their mass is about the same. What else is similar about them?
They both make up the atomic mass number.
There you go. Yeah, we add their masses together to get an atomic mass. That's also true. And the one thing we just mentioned, the very first thing, how are they similar? Very first thing we mentioned about them.
They're both in the nucleus.
They're both in the nucleus, right. So they're in the nucleus. They have approximately the same mass, and we add their masses together to bring up to calculate the atomic mass of an element. How are they different?
Protons have a positive charge while neutrons have a neutral charge.
That's right. So protons have a positive charge, and neutrons, we say, have no charge, no net charge. What else is different about them?
Doesn't the number of protons dictate what the element is, and neutrons don't?
Bingo. Yes. The number of, if you look at the periodic table, and hopefully you all have a periodic table with you. I've had this for quite some time now. You can see it's getting a little beat up. The number of protons in the nucleus determines what kind of element it is. So like I said before, if you lose an electron from the nucleus, you gain an additional proton, and it becomes a different element. For instance, fluorine would become neon, or iodine would become xenon. It would be the next larger element in terms of on the periodic table. What else does the nucleus? What else can the proton do that the neutron doesn't?
They can change the charge.
It has a charge. Okay, it has a charge. But what about the number of protons and neutrons? The number of protons gives us the identity of the element. What else does it give us? We mentioned the atomic mass before. So if we add the number of protons and neutrons, we take their mass, that gives us the atomic mass. What does the number of protons give us? Other than, of course, the identity of the nucleus, of the element.
The charge.
It gives us the charge of the nucleus, yes, but I'm sort of looking for something else. There's a certain number associated with the number of protons.
Electron?
Go ahead. I think you had it.
Ooh.
There's the atomic mass and the atomic
number.
The atomic number, exactly. The atomic number is equal to the number of protons. That's the atomic number. And the atomic number determines what element we have. So that would be the number here. So hydrogen has the atomic number 1. Lithium has the atomic number 3. That is the precise number of protons that that element has in its nucleus. Now, can it be the same? Can one element have the same or different number of neutrons?
Yeah, isn't that another difference? Like you can have more neutrons or less neutrons and it still be the same element. But if you
That's
change
right.
the
That's
protons-
exactly right. That is still the same element. An element can have, or a particular atom can have 17 neutrons or can have 18 neutrons, and it's still the same element. But if an atom has 17 protons and another one has 18 protons, they're different elements. So if the same element has a different number of protons, what do we call those?
Isotopes?
Isotopes, exactly. So isotopes are determined specifically and only by the number of neutrons. The number of protons is the same. Excellent. So what about number 2 here? So this is how we actually write the notation for a specific isotope. So what is A? What number is A?
Mass number.
Right. That's the mass number. So what is the mass number again?
Protons plus neutrons?
Right. So A is protons plus neutrons. What about Z here, or Z if you're from this side of the pond?
Atomic
Atom-
number?
What is it?
Atomic number?
The atomic number, right. And what is that?
Number of protons?
Number of protons only. Right. So if we were looking to see what element this is, the atomic number would tell us what a proton it is. And the atomic mass would tell us which isotope of that element it is. Now, what about X? What goes there?
The element.
The element, what element? The name?
Chemical element.
The symbol?
The symbol, right. So we wouldn't write copper there. What would we write instead of copper?
Cu?
Right, we would just put Cu. Anyone know why it's called Cu and not Co?
Doesn't it
No.
have something to do with Latin?
Because there's
There are, well, 2 reasons. Yes, it is very, very much has something to do with Latin. And Co is cobalt. So a lot of the elements that have been known for a really long time, most of the elements in the periodic table were only discovered in like the late 19th century. Once the whole idea of atoms, we sort of realized what they were. Once that happened, then this explosion of elements were discovered. But before that happened, there were a whole bunch of elements that had been known for like thousands of years. And copper was one of them. And it was known as cuprous. And potassium was known as K because it was known as the Latin name starting with K, which is like, I can't remember right off the top of my head right now. But you find these all over the place. Like lead, for instance, is Pb because it was called plumbum by the Romans, who used it for their plumbing. And it's a good element for doing, well, it's a good element and a bad element for plumbing because it's a soft metal. And so you could just, if there was a hole in a pipe, you could just put another piece of lead on it and hammer it, and it would seal it up. But as we know from Flint, Michigan, lead is not a particularly good thing to have your pipes made out of. So we've gotten rid of like most of the lead plumbing. Although even in some old buildings in San Francisco, buildings that were built before the turn of last century, you will find lead plumbing in a lot of them. So that's why we have these weird symbols that don't seem to make any sense. So let's look at number, oh, and C, we haven't done C yet. What's that?
The
All right, it is
charge.
Callion. Thank you, Adrian. It's the charge, exactly. So what is the what do we call this, and what do we call that? What will we call this?
Isotope symbol?
No, the whole thing together.
Carbon 12.
That's carbon 12. Now, it's an atom of carbon 12. What's this?
A
do we-
cation of carbon 12?
It's an ion, exactly. That would, yeah, very good. It's a cation. So cations are positively charged. And what are negatively charged ions called?
Anions?
Anions.
Anions, right. Oh, negative. And if I, used to have trouble trying to remember which is which, but if you think about cat lovers, they feel positively about cats. That's like the usual thing I have stuck in my head to remember the difference between those two. So what is the difference between an atom and an ion?
The atom has a neutral charge while the ion has a positive or negative charge.
Mm-hmm. And why? Why does it have a positive or negative charge? What's different about it?
Maybe because with the cation, it has less electrons than the normal atom.
Right. And what about an anion?
It would have more electrons.
Right. So the charge of an ion is dictated solely by the number of electrons, not the number of protons. That's really important to remember because the nucleus stays the same. So the nucleus is exactly the same, but the number of electrons is different. So if we have more protons than electrons, we wind up with a net positive charge. If we have more electrons than protons, we end up with a net negative charge. So that's really important to remember going forward, because I find a lot of students early on who haven't done chemistry in a while, or this may even be their first chemistry course, see something with a positive charge and say, well, protons are positively charged. They must have one more proton for a net positive charge. And that's true in a sense. I mean, if you have an additional proton, you have an additional positive charge, but you're now a new element. So if you have one more proton than electron, yes, you have a net positive charge. And yes, you are an ion, but you're no longer that element. You're a new element. You're the next one up on the periodic table. So let's have a look at some of these questions here. So as we already just mentioned, so the charge of an atom is determined by the relative difference between protons and electrons. Since neutrons don't have a charge, it doesn't really matter how many neutrons you have. They're not going to affect the charge. So what about this first one, 3A? What's going to be the net charge of that atom?
No charge.
0. It's going to have a charge of 0. So what atom is that?
Nickel.
Nickel, that's right. Nickel is a transition metal, and it is in period 4. So we've been learning the differences between groups and periods. We got there yet?
Yeah, I think on the video lecture she mentioned that.
Okay. Yeah, so the groups go up and down. Groups go up and down, and every element in the same group has similar chemical characteristics for reasons that will become hopefully obvious a little bit later. And periods go across. So period 2 would start with lithium and then beryllium, and then we go zzz, all the way across till we get to boron. So, and that will become obvious hopefully a little bit later too when we start talking about how electrons are organized. Now 3b, this one has 36 electrons and 35 protons. What would be the net charge there?
-1.
And what element is that?
Bromine.
Bromine. So we would put bromine minus. That would be the symbol we would use to represent that. And we'll find later that this is generally how we find bromine in the wild. It normally forms compounds where it becomes a negative, takes on a negative charge most of the time. Now, 86 electrons and 90 protons. What's going to be our net charge of that one?
4.
+4.
+4. Yeah, you always have to put the positive or the negative there. So we say it as a charge of 4. We don't know which is which. So definitely, yeah, +4. And that element would be, how would we write that ion down? What would be the symbol for that ion?
TH. +4.
TH, right. What element is that?
Thorium or something like that.
Thorium. Thorium, yes. Where do you think thorium was discovered? Just based on the fact that it's thorium.
Norway.
There you go. Exactly. That's the cool thing. One of the cool things about chemistry is whoever actually discovers it first, and sometimes there's a big fight about it, gets to name it as well. And so you will find that a lot of names in the periodic table are based on countries. Like GE is germanium, and CD is California, or CF is Californium. In fact, there are 4 elements named after Berkeley, because Berkeley was the site, and still is, of an atomic accelerator that basically invents new elements by smashing smaller elements into bigger ones and trying to fuse them together and make these massive elements. And so they've been doing this for a really long time. So there's californium and berkelium and lawrencium and americium also. So all discovered at Berkeley. All right, so that's clear. Let's go down to 4, clear these. So we have an ion with a +2 charge, atomic number, let's go to 4A. So now we're going to write the whole symbol. So we have an ion, has a +3 charge, 28 electrons, and it has a mass number of 71. So how do we figure out what element that is?
If it has a charge of 3+, that means it has 31 protons.
That's right. So what element is that? So we go to our handy dandy periodic table and we find out that 31 is
Gallium.
gallium, right. Oop. Where do you think gallium was discovered? It was named after Gall. Anyone know what Gall is?
On a golf course.
GAUL. It's what the Romans called France. And so it's discovered in France. So GA. Where do we put the 31?
To the left and at the bottom.
Right. Now it has a mass number of 71. Where do we put the 71?
The top left.
Mm-hmm. That tells us which isotope of gallium it is. And where do we put the charge?
Top right.
Yeah. So this basically tells us everything we need to know. Just by looking at this, we can tell how many protons it has, how many electrons it has, how many neutrons it has, what element it is, and what the charge is. And that's basically everything we would need to know about that particular ion. Let's do the next one. So we've got 36 electrons, 35 protons, and 45 neutrons. So first of all, what element is it?
Bromine.
Bromine, yes, bromine. We always put an "ene" on the end of that. So what are the things? So it's fluorine, chlorine, bromine, and it's not iodine. Every time I said iodine, I would get my knuckles rapped by my chemistry professor back in the day. Iodine, he was very, very, wanted to make sure that everybody knew that. And astatine, which is an interesting element we can talk about at some point. So yeah, bromine. So that is bromine. So what atomic number does bromine have?
35.
Right. And where do we put it?
Bottom left.
Yep, bottom left. Yep, that always tells us, we always look bottom left, immediately tells us which element it is. How many protons, that's its atomic number. Where do we put the atomic mass?
Top left.
Top left, and what is it?
80.
80, right. How did you get that?
I added the number of protons by the number of neutrons, so it's 35 plus 45 equals 80.
Yep, 80. And then finally, the charge. Where do we put the charge?
On the top right.
Top right. So we put negative or -1. Either one is fine. I generally just include minus because it's just cleaner. And if you just see a minus sign, you can just assume that just means 1. But this isn't wrong. If you want to include that, that's fine. So either one of those is correct. But you will find that most chemists will just put the negative sign there with the assumption that just means a single negative charge. All right, so number 3, we've got 86 electrons, a whole ton of neutrons, and a +4 charge. So first of all, what element do we have?
Thorium.
Man, we have thorium. Thorium again. Oop. Thorium, for some reason. Yeah, thorium. Right. So what's its atomic number?
90.
90. And how'd you get that?
86 electrons, and then if it's a +4 charge, that would mean that there's 4 more protons.
4 more protons, exactly. And where do we put, what's its atomic mass? The mass number?
232.
That's big, right? You will find, as we go along the periodic table, the number of neutrons increases faster than the number of protons. And that has something to do with the stability of the nucleus, and gets into some really bizarre physics involving the weak force and the strong force. And it's above my pay grade, let me tell you. But there are nuclear physicists working on this all the time. And that's one of the reasons why physicists are constantly making these new elements. You might think, what's the point of making all these like new elements? They only exist for like a femtosecond and then they're gone. Well, there's a theory that eventually we'll get to a point where these elements become stable again. So, because you'll notice that basically everything bigger than lead is radioactive. But the thought is once we get to like this really big atom, it will then become stable again. And everyone's racing to see, because whoever discovers that obviously is going to win a big time Nobel Prize. That's one of the reasons they're working on it. So that's our atomic number, sorry, atomic mass, atomic number. Where do we put the charge?
On the top right,
And what do we write down?
we write down +4.
+4. So +4 or 4+, again, it's sort of up to you. Either one is acceptable. And I've seen it both ways. So chemists, depending on where they are, where they live, where they went to school, either go +4, 4+. It doesn't, either one of those is acceptable. All right. And then finally, we've got +2 charge, 38 atomic number, and mass number of 87. So who's that?
Strontium.
Good old strontium. What's the atomic symbol for strontium?
SR.
SR. So where do we put the number, the atomic number?
On the bottom left, 38.
38. So our mass number is 87. We put it up here. And our charge there. Okay. So how many neutrons would that particular isotope of strontium have?
49.
49. Exactly. So we just, and anytime you need to know the number of neutrons, you could just do that. So you have your atomic mass, you subtract the number of protons, and it's already set up right there for you to figure it out. So it's like an easy shortcut. Okay. So I am going to send you into your, oh, do we have our TA here today? Are you with us?
Yes, I'm here.
Okay. Say hi.
Hi.
All right. So we're going to break up into groups and give you about, I don't know, half an hour to work on these. We'll work on 5, 6, and then these questions down at the end. I think we'll come back and we'll do 7 together. 7's kind of tricky. Have you worked on how to calculate average atomic mass? Hello. Have we done that already? Have you dealt with that in the lecture portion of the class yet? The difference between average mass and isotopic mass. Do we know what the difference is? You can either say yes or no, either one.
No. No.
Haven't done with that one. Okay. So we'll do that one together, but I'll just point out. So isotopic mass would be the mass of one atom that has that's a particular isotope. For instance, the isotope 16 here, oxygen 16, its mass is 16, which makes sense. It's not exactly 16, but it's pretty darn close. So one atom of oxygen 16 has the mass of 15.9949 atomic mass units. And the mass of one oxygen 17 atom is 1 atomic mass unit more, and 18 is 1 atomic mass unit more. But of course, when we're breathing oxygen in, are we breathing in just oxygen 16 or 17 or 18?
No.
No. What are we breathing in actually?
Carbon dioxide.
No, we breathe out carbon dioxide. But when we breathe in oxygen, we breathe in a little CO2 as well, obviously, especially if you're, huffing the tailpipe or something. But when we breathe in oxygen, we're breathing in a mixture, right? We're breathing in O16, O17, and O18. They're all mixed together. We can't separate them in nature. They're all there. But 16 is way more abundant. Almost 99.8% of all the oxygen you're breathing in right now is oxygen 16. And then this tiny fraction is 17, and an even smaller, tinier fraction is 18. But it's a mixture. And so if we look at the average, we have to take the average of all those atoms to figure out what the average atomic mass is. And that's what's given on the periodic table. If you look at the periodic table, right up next to the, let's see, it's a good one. So let's look at sodium here. So the sodium, the atomic number is 11. And then when we look to the side here, it gives us a number, and that's the mass. But we notice that pretty much all of the masses aren't exactly a number. When we're dealing with isotopes, we say that they have a precise number of protons and a precise number of neutrons. But when we look at at a whole bunch, at a whole mixture of elements that has all the mixture of isotopes, they don't all have the same number. Some of them have more neutrons, some of them have less. And so this is the average mass. So the isotopic mass would be the mass of one atom of an element, and the average mass, which is given on the periodic table, is the average of all of those isotopes mixed together. And so we'll go in how to calculate that at the end. Okay, does that make sense to everybody? You can't separate these things in nature. They're all together because they're chemically identical. Oxygen 16 gets turned into CO2 in your body, exactly the same as oxygen 17 and 18 do. There may be very tiny differences in how they react, but the differences are incredibly small. So there's really no way to separate them. So the average mass is the mass of all of them together. And it depends on how abundant they are. Okay, so I'm going to break everyone into groups. We'll spend about, like I said, about 30 minutes doing these. Remember, you want 1 or 2 people to present answers at the end. So in the group, you may want to just break up the questions. Each person work on a specific question, or you can all work on the same question at the same time if you like. So we're going to do 5 and 6, and then mole and molar mass. Unless, so have we really started the topic of moles yet in lecture? It's super important. Could someone define a mole for me? What is a mole?
Isn't it like how many particles of an atom?
How many particles of an atom? It's definitely it's a number.
It's a measurement.
A measurement of what? It's a unit. Yep, that's true too. Unit of what?
Of a substance.
Mm-hmm. So what does it mean? So yes, it's a unit of a substance. That is definitely true. It's a unit of a substance, but it isn't a mass, is it? It is a mass. I mean, we can associate a mass with it, but a mole is different from like a gram. So the way I define it, it's a reactive unit. Basically, 1 mole of an element reacts with another mole of an element. That's how reactions take place, in molar ratios, not mass ratios. So when you have hydrogen and oxygen coming together and making water, we say that 2 moles of hydrogen gas react with 1 mole of oxygen to give 2 moles of water. That's how it works. So I just think of them as reactive units. So we think of, that's how reactions take place. They do not take place with atoms, with grams. So we can't say that 2 grams of hydrogen reacted with 1 gram of oxygen and we got 2 grams of water. That didn't happen. That will never happen because it's atoms interacting with atoms, moles interacting with moles. And we use moles because we can't measure atoms. Atoms are way too small for us to be able to measure. Moles we can measure. So what is the mass of a mole? So if I wanted to know, let's say here's a mole of oxygen. What would be the mass of a mole of oxygen?
.022 times 10 to the 23rd power.
That's the number of atoms in a mole. That does not tell us the mass. So you're right. That's the number of that's the number of molecules of oxygen in a mole. But we still don't know what the mass is. And remember, if I go into the lab, I can't measure the number of molecules. They're way too small. I don't have a balance where I can like weigh out, 6.022 times 10 to the 23rd atoms of copper. I can't do that. But what can I measure to give me moles of copper? So if I wanted let's say I want a mole of copper, for instance, how would I measure a mole of copper?
In grams?
Exactly. In grams. Grams I can measure. I can measure grams all day because I've got a balance. I've got some copper that's been all ground up into like a nice powder. And so I want to weigh out a mole of copper. How much would I weigh out to give me my mole of copper? How would I determine that?
Does 1 gram equal 1 mole?
It does for one element, yes. But that's the only element that's true for. Every element is going to have a different mass for its mole because every element has a different size of atoms. So if like an atom of hydrogen has 1 proton and 1 electron going around it. So that would be the mass of 1 atom of hydrogen. On the other hand, oxygen has got 8 protons, 8 neutrons, and 8 electrons going around it. So it's 16 times bigger than hydrogen. And so a mole of oxygen atoms should be 16 times bigger and weigh 16 times more than a mole of hydrogen. So how do we find out? Looking at the periodic table, I can easily determine what the mass of a mole of an atom is. So what do I use to figure that out? There's a number right on the periodic table that tells me how much a mole weighs. How do I figure out what the mass of a mole is from the periodic table?
Is it from the atomic mass?
Exactly. The atomic mass tells you in grams how much a mole of that atom would be. Excellent. So that's why we need the average atomic mass, because when I'm pouring out my copper and I'm trying to figure out, and I want to weigh out a mole, it's going to have all the isotopes of copper in there. It's not going to have just one particular isotope. That takes a lot of work to separate just that one particular isotope. It's going to have all of them in there. So I need the average mass of all of them together. So if I want a mole of copper, what's going to be the mass of it? How many grams is that? Hopefully you have your periodic table. If you don't have your periodic table in front of you, you should next week, okay? Or you can just look it up online, get a periodic table. So what's the average atomic mass of copper?
63.546.
There you go, 63.546. Meaning all of the isotopes together of copper, and there's a couple different ones, in different abundances, but when I average them all out, 6.022 times 10 to the 23rd atoms of copper weigh precisely 63.546 grams. So when I weigh out my 63.546 grams, I now officially have 1 mole of copper. Now, what about O2? Let's come back. Now, O2, is that an atom or a molecule?
Molecule?
That's a molecule. Excellent. Because that's 2 atoms together. Oxygen would just be by itself. So what would be a mole of O2? What would be the mass of a mole of O2? How do we figure that out?
31.98.
Excellent. How'd you get that?
So wouldn't you multiply the atomic mass number by 2?
Bingo. Yeah, excellent. Yeah, so you look up the atomic, you just go to oxygen, you look at oxygen. That's 15, oh man, I got a little water stain there. 15.999 or 998, one or the other. But remember, all these atomic masses on the periodic table are of atoms. And we'll find out that pretty much all of these elements up in the top left-hand corner don't exist as atoms. They exist as molecules. Like for instance, we don't breathe oxygen atoms. That would be really, really quite bad for us because oxygen atoms are super reactive. We breathe oxygen molecules. So oxygen is O2, fluorine is F2, nitrogen is N2, chlorine is Cl2, iodine is I2. Basically, they all exist as what we call diatomic molecules. So just for instance, same thing here for fluorine is F2. That's the way it exists in nature as itself. That's the most stable form of fluorine is F2. Fluorine atoms are super reactive. And so fluorine molecules are dangerous enough. Fluorine atoms are super, super dangerous because they're so reactive. So why don't we come back? Why don't we just do in the groups, we'll just do the 2 tables, and then we'll come back and we'll talk about the mole and molar mass. That appears to be a relatively new thing, okay? So I will send you into the groups. Basically, just complete table 5 here and table 6. So I'll give you like 20 minutes to work on it. Then we'll come back and we'll look at the topics of mole and molar mass together. Does that sound like a good idea?
Yes.
Yes.
Yes, everyone agrees. Hooray. Okay, so let me get this together here. Okay, everyone's back together. Love it. Okay, so hydrogen 2 it basically goes through what the atomic number, the mass number. And as I mentioned to one group, can you remember what hydrogen 2 actually has a chemical name? Do you remember what it was?
Deuterium?
Deuterium.
Oh,
Yes,
deuterium, there you
deuterium. And when deuterium makes water, instead of saying, and it also we give it a chemical symbol. We give it the chemical symbol D for deuterium. And when deuterium makes water with oxygen, we also call it D2O. Anyone know what D2O is also known as? You've heard of it.
What was the question?
What is D2O also known as?
H2O?
H2O is regular water, and D2O is,
Deuterium oxide.
also known as what kind of water?
Is it distilled water?
Nope.
Nope. All right, never mind.
Heavy water. Heavy water. Yep. So when you hear about heavy water in nuclear reactors, that's what it is. It's deuterium instead of hydrogen. So the name. So let's look. So group 3. Let's do the first one here. So 3H. What would we call that?
Hydrogen 3.
Hydrogen 3. Right.
Oh, sorry. Did you say group 1? Like meaning like?
As long as I get the
The breakout
answer,
room?
I don't care. So hydrogen 3 also has a name. Do you remember? Same group. Do you remember what hydrogen 3 is called?
3.
Tritium.
Tritium. That's right. And we give it also as a chemical symbol T, which is used sometimes. And tritium is also radioactive, whereas hydrogen and deuterium are not. So what's the atomic number of hydrogen 3 or tritium? Anyone can just jump in with these.
1.
1. And so, I'll just go through. So group 2, what's the mass number for tritium?
3.
3, exactly. That's where the name comes from. So whatever the name is, the chemical name tells us basically what element it is, and by definition, how many protons it has. So we already know how many protons it has. What we need to know is how many neutrons it has. And so we give it the mass. So how many neutrons would hydrogen 3 have? Group 4. Good old group 4. Group 4. Group 5.
I.
How many neutrons in
2.
2.
2? Yeah. 1 proton, 2 neutrons, give you a mass of 3. So how many electrons would hydrogen 3 have?
1.
1, exactly. It's an isotope. Isotope is the same number of electrons. It's the same number of protons. It's the same number of electrons. So chemically, it is the same. Only the neutrons are different. And so what charge would an atom of hydrogen 3 have?
Positive.
Got 0.
0, because it's an atom. Right. An atom has no charge ever. So if I say an atom of helium, an atom of carbon, an atom of iron, an atom of strontium, it has no charge because I didn't call it an ion. That's the difference. So an atom is always charge is 0. It's always neutrally charged. So group 6. So if right here, what's the name of this particular atom? Actually, it isn't an atom, is it? It's an ion. What's the name of it?
Sodium.
Sodium what?
22.
Sodium 22. Yep. So what's its atomic number?
11.
Mm-hmm. Because no matter what kind of sodium it is, they all have 11 protons. Now, what's the mass number?
22.
Yes. Therefore, the number of neutrons is
11.
11. And the charge is
10.
10
I got 1 plus 1.
Positive 1.
plus 1. Yes. Plus 1 because it has 10 electrons and 11 protons. So it has a charge of plus 1. All right. So group 1, take me through carbon 12 here. What would be the symbol?
C.
It'd be C
Mm-hmm. And where do I put the 12?
at the top.
At
Top
the top.
left.
What would I put at the bottom left?
6.
6.
6. There you go. So what's its atomic number?
6.
6. And so the mass number is
12.
12. So the number of neutrons is
6.
and the charge is 6 electrons.
0.
0.
None. Yep. All right, group 2, carbon 13. Let's go through the same thing. What would be the symbol for carbon 13?
13C.
Yep. And we can put the 6 there if we wanted. So its atomic number is
6.
6. Mm-hmm. Mass number?
13.
Uh-huh. Neutrons?
7.
7. And what about the charge on that one?
0.
Also 0. Right. Argon 40. So group 3. Give me argon 40.
Are we looking for the symbol, the number?
Yep. Symbol.
Oh, okay. It's the one at the top's gonna be 40,
Mm-hmm.
and then the bottom number, I guess, the 18.
Mm-hmm. And what's the symbol?
None. It's just an atom.
But it still has to have a chemical symbol, though, right?
Oh, I thought you meant the number. Sorry. It's the AR.
R. That's right. It's the pirate element. Okay, so we know its atomic number is 18. And the mass number is
40.
40. So it has how many neutrons?
22.
Yep. And so it has 18 electrons, and its atomic number is 18. What's the charge?
0.
None. Excellent. Okay, group 4. What is the name of the element here with atomic number of 7 and 8 neutrons? What element is that?
Is this nitrogen? Nitrogen.
Nitrogen. That's
Oh,
right.
nitrogen.
Nitrogen. Which isotope is it?
It's 15.
15. Mm-hmm.
15
So what would be the symbol we give that?
is nitrogen 15.
That's the name. What symbol do we give it?
15N.
15N. Uh-huh.
Um,
So we know its atomic number is 7. What's the mass number?
the mass number is 15.
Right. And so does it have a charge?
It's a -1.
Right, because it has one more electron than proton. So that would be -1. Excellent. So group 5, let's do the last one here. What element are we dealing with? What's the name?
Beryllium.
Beryllium. Yes.
Yeah. Beryllium 9.
Right, it's a mass number of 9. So we call that beryllium 9. So what symbol do we give it?
Be.
Be.
With the 9 on the top left.
Yep. So how many neutrons does beryllium 9 have?
5.
5. And does it have a charge?
plus 2.
Yeah, and you'll find that beryllium, as when it becomes an ion, has a charge of plus 2. Why? Because it's in the second column. It's in the second group, and we'll get into that a little bit later as well. When we talk about electrons in more depth. Okay, let's super quickly. Again, I'm sort of running out of time here. So, atom 1 and atom 2. So group 1, what's the relationship between those two? Are they isotopes, same atom, but not isotopes? Or are they different elements?
I put the second one. Same atom.
Atom, not isotopes. Okay, why don't you think they're isotopes?
Well, the mass number, or the 12 and the 13 is different.
Right, so that means they're the same atom. That's true, because they're both C, they both have the same number, but why aren't they isotopes?
No, I'm not sure.
They are isotopes because isotopes have a different mass, but they're the same number of protons. So 6 tells us how many protons there is. And so 6 is the number of protons. That automatically tells us it's carbon. Carbon is the only element with 6 protons. So it's carbon. So it's the same atom, but because the masses are different, they have different numbers of neutrons. But neutrons don't add anything to the charge. They don't change the charge of the nucleus. And if the nucleus has the same charge, it's the same atom, but they're different isotopes. That's the definition of isotope. Same number of protons, different number of neutrons, okay? What about the second one, group 5? Let's go to group 5. The second one here. Are those the same atom, but different isotopes? Same atom and same isotope, or are they different elements entirely? Group 5.
I put same atom.
Yeah, they're exactly the same.
Yeah.
They're both carbon, which means they both have 6 protons automatically. And this one has a mass of 12. This one has a mass of 12. They're exactly the same. Excellent. What about group 6? What's the difference between argon 40 and argon 41?
Aren't they isotopes?
They're isotopes, right. They're both argon, so automatically they're not different elements. So we know that can't be the case. So they're the same atom, but are they the exact same atom, or are they different isotopes? Well, the mass tells you that they're different masses, so they have to be isotopes. Yeah. Excellent. All right, so let's look. Oh, actually, we still have two more. I'm just going to assume you guys got those. I'm going to do a couple of these with you. We'll do 7 together, and then I'm going to leave you to do the rest on your own. So, quickly, number 1, I have a mole of hydrogen gas, which means I have a mole of molecules, not atoms. I have a mole of O2 molecules. I have a mole of F2, fluorine molecules. Which has the largest number of molecules of those 3? They have 1 mole of each one.
Fluorine.
Fluorine. Okay, why is that? That's the explain why part.
Is that the biggest atomic mass?
It has the biggest atomic mass, yes. So that's the answer to B, right? Wouldn't that be the answer to B?
No, because it would be the opposite.
Why is that? So a mole of fluorine would have more molecules in it than a mole of hydrogen? What's the definition of a mole?
Yeah. A mole of fluorine would have more molecules than a mole of hydrogen, but that means that hydrogen has a greater mass because there's less molecules in a mole. So
But
meaning
hydrogen doesn't have a greater mass. We know that because hydrogen is a mass of 1, right? Hydrogen is a mass of 1. And fluorine has a mass of, where are we? 17, 16, 18, 19. Fluorine is a mass of 19. So fluorine's 19 times bigger than hydrogen. So fluorine, a mole of fluorine would have 19 times the mass of a mole of hydrogen. What about the number of molecules, though? What's the definition of a mole? How many molecules are in a mole? That's where our old friend Avogadro comes in. What does Avogadro have to say about this?
6.022 times 10 to the 23rd.
That's right. When I teach this particular class, I generally don't even mention Avogadro's number because it just confuses people. But in this instance, it tells you exactly how many molecules are in a mole, or atoms. If it's a mole of atoms, it's the same number. If it's a mole of molecules, it's the same number. It's always the same. So every single mole anywhere has this many particles in it. All of them.
Oh, so A is a question?
What was that? So that, yeah,
So A is a trick
so that's
question?
the answer to A. Which is the largest number of molecules? They all have exactly the same number because they're all a mole. And a mole by definition has this many molecules in it. Now, the reason I don't use that number a lot is because it really doesn't come up very much because we don't count molecules generally. It's too difficult to count molecules. What I can do is determine mass. So which one of those would have the greatest mass? A mole of hydrogen, a mole of oxygen, or a mole of fluorine?
Fluorine.
It's got to be the fluorine, right? Because it's the heaviest. It has the biggest mass. So what would be the mass of a mole of fluorine? How would we calculate it? I see someone's already put it in the chat. Thank you very much. Adrian, how did you get that?
So the fluorine has 18.998 mass.
Mm-hmm.
Then times 2.
Times 2. Right. So 1 mole of fluorine atoms is the average atomic mass of fluorine. Now that number, the average atomic mass, has 2 meanings. That's the atomic mass units of 1 atom. But like as I said, we can't measure the mass of 1 atom. We don't have a scale that small. But we can measure a number of grams. It's also the number of grams of a mole. That's the great thing about the atomic mass. It's the mass of 1 atom in atomic mass units, and it's the mass of 1 mole in something we can measure, which is grams. So let's look at number 2. Which would have the greatest number of moles of oxygen atoms this time? So we have ethanol, which is this one. We have formic acid, which is this, or we have water. Now we have 1 mole of each one. Which one has the most number of moles of oxygen atoms?
Formic acid.
Why is that?
Because it has 2 moles.
There's 2 moles of what?
Of oxygen.
Right, it has 2 moles of oxygen for every mole of formic acid, which is the same way of saying it has 2 atoms of oxygen for every molecule of formic acid. So if I have a mole of formic acid, there's 2 moles of oxygen in there. If I have a mole of water, there's 1 mole of oxygen atoms in there. Same with ethanol. So how do we calculate the molar mass of a molecule? How do we go about doing that? So if I have silver sulfate, so that's the molecular formula for silver sulfate. What does the molecular formula mean? What is that telling me? So I've got silver sulfate, Ag2SO4. What is that saying? What do those numbers mean?
Would you multiply each of the numbers by Avogadro's number?
That would give me the number of atoms in a mole. That's not really going to help me. What I want is the mass of 1 mole of that.
Oh, so
And the mass is, and remember, mass is in grams. Mass is not a number. Mass is a unit of measurement. So we want if I have 1 mole of this, how many grams of it? How many grams is that? So what I'm starting with, this is a molecular formula. What do those numbers mean?
2 atoms of, I don't know what Ag is.
Ag is one of those old, we've known about that element for a really long time. So it has a Latin name too. It's silver. Ag is silver. Ag is silver, Au is gold, because both of those precious metals have been known for a really long time. So they have really old names. So that is silver. So, right, so if I have 1 molecule of silver sulfate, it means I have 2 atoms of silver. So I would go 2 times silver. How many atoms of sulfur do I have?
1.
1. So 1 times sulfur. And how many atoms of oxygen do I have?
4.
4. Right. Now, so how much does a mole, so if I have a mole of this stuff, how much does a mole of silver weigh? How would I figure that out?
The atomic mass, which is 107.87.
Bingo. Right. I just go to my handy dandy. I go to ptable.com, which I put that in the chat. It's an excellent place to find out about things. Or I have my handy dandy printed out periodic table. I go down to silver. Where is it? Where is it? Yeah. So that's 107.858. 107.858 grams. Because atomic mass units does not help me. I can't measure atomic mass units. Grams, I can do that. So 1 mole of silver sulfate would have 2 moles of silver, and each one of them weighs about 108 grams. Now for sulfur, who can give me the atomic mass of sulfur? Adrienne, you're all over it. So what's the mass of a mole of sulfur?
Is it 32?
Now we don't want to limit ourselves. We don't want to limit our precision.
Oh, right.
So we would want to. So whatever more accurate mass we can find, we would use that. And remember, do we want the average atomic mass of sulfur, or do we want the isotopic mass of sulfur? Oh, I see we've gone over time again. Yeah, if people want to go, you can go ahead and go. I'm going to keep going for about 10 minutes, and then we'll shut down. Thanks. So sulfur, do we want the average mass or the isotopic mass? So in other words, do we have a particular isotope of sulfur or do we have
Average.
all the isotopes of sulfur?
Average.
Average, we have all of them, right? We can't separate them. So any sulfur we have, any amount of sulfur we would have, would contain all the different isotopes. So we need the average mass. So what's the average mass of 1 mole of sulfur? That's what's going to be on the periodic table. So yeah, Jean says 32.06. I've got 32.066. So we'll just use that one, 066 grams. And what about oxygen? I got 4 moles of that. So what's the average atomic mass of 1 mole of oxygen atoms? Now remember, these are oxygen atoms, not oxygen molecules. Oxygen molecules are O2. This is O4, meaning 4 moles of atoms. John again to the rescue. Yeah, 15.999. So all we do is just multiply these together and then just add them all up. And if we do that, someone's done the math already? I can hear clicking. Kenneth got 311.799 grams per mole. So the molar mass would be 311.799 grams. Now, there's no reason to round that because remember, 1 mole, 1 is a count. It's not a measurement. So we would want to know the mass of exactly 1 mole. If, on the other hand, we were given a measurement like 1.0 moles or 1.01 moles, we would then reduce it to the right number of significant digits. But since we were saying 1 is an account, we would give as many significant digits as necessary. All right, let's do one. Oh, let's do the last one and we'll call it a day. Anybody have any questions about the moles? I mean, I'm sure there's going to be a lot of questions about it, but anything that's confusing you now about the whole molar concept? You want to do one more molar question before we do the last one?
Yes,
Sure.
please.
Okay, sure. All right, let you pick one. 4 or 5?
Four.
Sure, let's do 4. Because this is a classic changing of converting units question. So it's got two parts. It's figuring out what the mass of potassium bromide is, then doing a unit conversion. So we're doing both. So we want the number of moles of each type of atom in potassium bromide. All right, so 2.2 grams. So let's go back to our whiteboard. So we have 2.2 grams KBr. And we'll find out when we're naming these compounds. You start with the element further to the left on the periodic table. That is potassium. And we end with the element further to the right on the periodic table, and that is bromine. And then for the first element, we just give it the full name, potassium. And then the second, we finish with an "ide" suffix to say that it is the second part. So we have 1 So so if we have 1 mole of KBr, how many moles of potassium and how many moles of bromine do we have in that mole? So if I was to have 1 mole of this, how many moles of potassium atoms, how many moles of bromine atoms? Right, 1 of each. Exactly. Exactly, John. One mole of each. Because in 1 molecule, we can assume that there's a 1 there and a 1 there. If there's no number, we just assume, we know that it's 1. We don't bother putting a 1 there. So I have 1 K and 1 Br. That means that's it. Then they make a molecule. When I split it apart, I have a mole of each one. That's how we're going to figure out the molar mass of KBr, potassium bromide. So what is, we have 1 mole of potassium and we have 1 mole of bromine. What's the mass of 1 mole of potassium?
$39.0983.
There you go. 39 point, right there. 0.098. Ooh, you even got the 3. Excellent. And 1 mole of bromine is how much?
79.904.
79.904. Yep. Grams. So we just add them together to get our, that's the mass of 1 mole of both of them together. So what's the mass of 1 mole? Don't make me do math, people. That's just rude.
$119.0023.
0023. Right. So if I had 1 mole, and this is a salt. Actually, this is sold as a sodium substitute. Actually, that'd be potassium chloride. Never mind that. So sodium chloride is table salt. And then for people who have trouble with high blood pressure, sometimes they will put KCl or potassium chloride on their food. And believe me, potassium and sodium do not taste the same. Sodium just gives you that nice salty taste. Potassium does not, strangely enough. Right, so 1 gram, 1 mole is 119.0023. So to answer the question of how many moles do we have in 2.2, we need to convert the units again. And we did lots of these unit conversions last week. And this is a unit conversion you'll be doing for the rest of your life if you continue in chemistry. So remember, the way I like to do these is you start with the unit you have and you want to get to the unit you want. So the unit we have to start with is our 2.12 grams. Now we want to multiply that by something to get us to moles, because that is the unit we want at the end. So what are we going to put in the numerator and what are we going to put in the denominator to get us from grams to moles? What goes in the numerator?
1 mole.
1 mole, exactly. That's the unit we want, so that goes up top. And what unit do we want to get rid of? We want to get rid of which one?
Grams.
We want to get rid of grams, so we'll put that in the denominator. 0.023 grams. So my grams go away. I'm left with moles. I'm happy about that. So what is my answer? How many moles do I have in 2.12 grams?
I have 0.0178147.
Okay, hang on. Let me keep up with you. So 0.0
1781.
1781 moles. Now we're almost done. What's something we have to take into consideration now?
Sig figs?
Sig figs. Could never get away from sig figs. So in this instance, we haven't got a count. We weren't saying give me exactly 1 mole. We weren't counting the number of moles. Now we're measuring the number of moles because we're given a measurement to start with. So we've measured 2.12 grams. And we want to convert that to moles. So we're limited by a measurement. If you're not given a count and you're given a measurement, you're limited in precision by whatever the precision of that measurement was. So how many significant figures do we have in our measurement?
3.
3, right. 1, 2, 3. So we have 3 sig figs. We can't give any more than that because we're limited by the precision of the mass measurement. So giving 0.01871928643 is meaningless because we can't give a number with more precision than the one we start with. So we would have to round our final answer to the same number of significant digits, which is 3. So what would be our final answer? For number of moles?
0.0178.
Yep, bingo, excellent. Yeah, that would be our final answer. So if you were to put this on an exam, you would lose half a point or something. Your answer isn't wrong. Numerically it isn't wrong, but it has too much precision that you can't justify this one because we haven't measured the mass precisely enough to justify it. So you'd have to leave it off to give a more accurate scientific answer. All right, let's do one more problem and call it a day. Let's go. So what I'll do is we'll do number 6 because they give you an insight into number 7. Number 7 is going to be a little tricky, but I can sort of point you towards it. But number 6 basically shows how you calculate average atomic mass. So gives you all this information. So gas picked up from a meteorite shows that it had 3 different kinds of neon in it. So 3 different kinds of neon atoms were found in there. So we have neon 20, neon 21, and neon 22. So we want to know what's the average atomic mass of neon in that sample. So how do we go about doing that? So let me write this information down so I can, so 91.7, 19.924. 1.4. All right, got all the information down. So when we do a average, we have to take into consideration 2 things. What's the distribution of those 3 different atoms? Now, the thing is, in any element, the number of isotopes is not going to be evenly distributed. So if I have carbon 12, carbon 13, and carbon 14, which all exist, as well as a tiny amount of carbon 15, that doesn't mean that 1/3 is carbon 12, 1/3 is carbon 13, and 1/3 is carbon 14. So we can't just all add the masses together and divide by 3 because that's not the distribution. So we have to take into consideration what's the distribution of each one of those atoms as well as the mass of each one. So if we look at the three different atoms of neon, so we had neon 20, 21, and 22, right? So the mass of neon 20 was 19.9924. The mass of neon 21 is 20.9940. And the mass of neon 22 is 21.9914. Now, they're not evenly distributed, like I said, so we can't just add them all together and divide by 3. We need to multiply them by something. Now, the first neon was present at 91.84%. The second one was present at 0.47%, and the third one was present at 7.699%. So what are we going to multiply these three things by to give us their actual distribution?
You would multiply the number in pink times the number in purple and then add them together.
Exactly. So what do we multiply the mass of neon 20 by?
91.84 times 19.9924.
Nope. You're close.
Wait, did I read it wrong or am I in the wrong place?
We're not going to multiply it by 91.84. What are we going to multiply it by?
Oh, because it's a decimal. You change it.
There you go. Right. Exactly. So what do we multiply it by?
0.9184.
Bingo. Yeah. So we need to convert the percentage to a fraction, because that's all a percentage is a fraction times 100. Well, we don't want to multiply it by 100. We want the actual fraction. So we turn it back into a fraction. So that one we multiply by 0.184. What did we multiply the 21 neon by?
0.0047.
Mm-hmm. And the last one?
That would be 0.0769.
Are you sure?
0.
Remember, we're dividing by 100, so we move it 2 decimal places. 1, 2.
Oh.
Yeah. Yeah, so each one of these, we just multiply the mass of each ion, or of each atom, by its distribution, by its fraction of the total. That's all we're doing. So this, we just add this and this and this. We just add them together, and then we get what's our answer when we do all that?
20.508.
20.508. Keep going.
15.
15. Keep going.
Wait, no. So it's 1508. Sorry.
Oh, oops. So 20.1508.
3062.
3062. Now, figuring out how many decimals is going to be a little trickier, because remember, this is going to have 4 significant digits. This is only going to have how many?
2.
2. And this one is only going to have 3. But remember, when we're adding them, we basically, we're just looking at the number of significant digits past the 0. So this would only have 2 significant digits past the 0. This would have 4 significant digits past the 0, and this would have 3 significant digits. So we'd have to look at the number of significant digits past the 0. But basically, yes, you just add them all together. And so the numbers would be 20.15 atomic mass units. Now, how much would a mole of this neon, what would be the mass of a mole of this neon? Because obviously they didn't get a whole mole, because they're just got this tiny, tiny amount.
So would you multiply that by the atomic mass number of neon?
Nope. If this is the atomic mass number, so remember, that's just AMU, atomic mass number. So how many grams per mole is an atomic mass unit? It's the same number. Because remember, AMU just stands for grams per mole as well. So it would be 20.15 grams in a mole. It's the same number. Yeah, it's the same number. Just that AMU is pretty much a useless number to us because we can't measure that directly. Can measure grams though. Although I think you had some questions about mass spectrometry earlier. In that we actually can measure atomic mass units. I did mass spectrometry for a really long time. So I had instruments that could measure AMU. But generally when you have if you're working at home and you've got a scale, you can't measure AMU. We can measure grams. So I'm just going to give you a sort of hint of how to do the last one, and then we'll wrap it up. So let's look at the last question. Last question is a doozy. So we got 3 isotopes of oxygen. And the question is, what's the percent abundance of, where's my annotation? Here we go. What's the percent abundance of 17 and 18? Well, man, you're looking at this, how the hell am I going to figure that out? Well, the way to figure that out is to consider the percent abundance of 16 is 0.99757, right? That's the abundance of oxygen 16. Now let's say the abundance of oxygen 17 is X. Don't know what it is. So we're just gonna have to solve for X. So if that's the case, what's the abundance of 18? Well, we know that the abundance of 17 plus 18 equals 1 minus 0.99757, right? Because the abundance of all 3 of them is going to be 1. The abundance, the fraction of that's 16 is this. And so whatever's left over is the abundance of both of them. And the abundance of both of them is going to be, let me figure this out here, minus 0.99757. So the abundance of both of them together is 0.00243. Now one of them is already X. We've already said that X is 17.0. And so the abundance of 18 is 0.00243 minus X. 0.243 minus X. Solve for X. Okay. Now we'll be posting the actual answers for these in a couple days. But that's when I saw this question, I was like, oh man, how do you go about solving it? And then it's like, oh yeah, it's very clever. It's hard, but it's hard to sort of work your head around. But then once you've figured out how to solve for X, then it's just, filling in, doing some math.
So to solve for X, would you take into account the atomic mass number of oxygen and then work from there?
Right. What's the average? Right, exactly. What's the average mass?
15.999.
Or if you can find more digits than that. So that's what you would start with. So exactly. So this plus this together equals 15.999. So then yeah, solve for x. That's I don't know. It's if you really like doing these sort of puzzle questions, you're gonna like this. If you don't like doing algebra, if you don't like doing algebra, you're not gonna like chemistry very much. Because there's a ton of algebra in it.
So, Professor, the
Yeah.
percent abundance of for the second one, it's x. Will you just leave it there, or do you have to solve for x?
You need to solve for x, and then once you solve for x, you figured out the abundance of 17, and then you know what the abundance of 18 is as well, because you've solved for x. So then x, you just subtract 0.0243. You subtract x from it, and that's going to be your percent abundance of 18, and you're done.
Oh, so the whole percent abundance equals 1.
Exactly. Yeah, it has to, right? I mean, if those are the only 3 isotopes, those 3 things have to add up to 1. Yeah.
Okay, thank you.
That's where we got this expression. So the total abundance is 1. The abundance of 16 is this. And so the abundance of the other 2 things must be the difference. That's where we got 0.00243. That's the abundance of the other 2 added together.